Good evening, physicists. This is lecture 3 of topic 3 of unit 3. A lot of threes there, bending waves. This video is going to be going through the main ideas of chapters 4.5 of book 1, or chapter 4.5 of book 1. Please complete this reading before class. Here are your learning intentions and success criteria. So we can see here students will be able to explain the wave phenomena of refraction and diffraction, and we've got our 3 success criteria there. Have a read through, complete the KS table down there on the right. Okay, hopefully you've got that done. So you can see here we've got a definition, an explain and a compare, so a lot of knowledge type verbs there. So if we're going to define something, we need to know what it is. So what's refraction and what's diffraction? Now look here, we've got to explain these using an idea called Huygens Principle, and if we don't know what it is, it's pretty hard to be able to use it to explain anything. And the last bit is comparing differing slits and wavelengths, so diffraction in relation to these two things. So how do slit size and wavelengths affect diffraction? Not much doing on this one. So let's start with Huygens Principle. Now, I am not Danish, I can't pronounce his name correctly, but we'll just call him Huygens. So, in the 1600s, scientists were studying waves and light, trying to explain the cause of different phenomena they'd observed. Now remember, the difference between a law and a theory is the law is the mathematical observation, and the theory is the explanation of the why. So we've got a law of gravity, but we don't have a theory of gravity just yet. And so Christian Huygens, who was a Dutch scientist, as I said, he developed an idea for how waves propagate, how they spread out. And he said the vibrations at one point causes the particles next to it to vibrate in harmony. So in harmony in this case means at the same oscillations and the same sort of pattern, or at least connected to it, which causes the particles next to that to vibrate, and so on. Okay? And so the definition I provided for you there, and here is sort of a representation of Huygens with a diagram. So he basically said that every part of a wave acts as a point source. So it's a single point that is the source of a wave. And as the wave moves forward, it creates new point sources. And so here we've got, for example, here's a wave front, this inner line here, and they've just chosen a few points. Now, every single point on those, and remember points are infinitesimally small, would be considered a wave source, or a wave front, a point source as well. But we're not dealing with calculus, so we're not going to do any mathematical formulas to show this. We're just going to sort of represent it in the abstract here. And here they've each created a small wave that has spread out from it. You can see this sort of half circle there. There are the thicker lines. And what this diagram has done is gone, okay, let's connect up all these wave fronts to create a new, bigger wave. Now you might go, but there's gaps in it, and it doesn't really be straight. But remember, we've only drawn 8-ish dots on there. In reality, you would have an infinite amount of dots, and so you'd have an infinite number of wavelets, these little waves. And if you took all their amplitudes at a certain point, you'd be able to, or a certain point in time, you'd be able to go, oh well, I can see clearly here's this ring pattern around it. Now, the problem is this sort of explained why they occurred, but it didn't say, didn't give any evidence for why the method was correct. It predicted things really well, and it explained, it matched, the explanation matched all the observable phenomena, but it was sort of like an insight. It was a leap of almost faith, and going, this is why it is, but I can't explain it why, it just works. Now go forward a few hundred years to today, and we have this thing called path integrals, which I'm not going to deal with at all in this unit, and you're not probably going to see it at all at university until university. You will have done in Year 12 a bit of integration, I imagine, by now, but it wasn't until a couple hundred years later that the development of path integrals in quantum mechanics and some of the assumptions required in that showed Huygens' insight to be correct. Okay? Now, in the 1800s, a scientist by the name of Fresnel, he worked with Huygens' principle to show that his work with lenses and diffraction and interference combined with Huygens could also explain diffraction effects. So Huygens figured out reflection and refraction, but he couldn't explain diffraction. Fresnel figured that part out for him. So let's start with reflection. Oh, that's weird, my animation kicked in straight away. There we go. So this is Huygens' principle applied to reflection, and as you can see here, it is very, very complicated to look at. You don't need to explain why. It doesn't say anywhere why, asking you to explain why the law of reflection, that incident angle equals reflected angle, is true. So we're not going to do Huygens on reflection. Stop that. We're going to go into refraction. So, refraction is a property of waves that requires a 2D medium to observe. Okay? It involves a change of velocity, but also the change of direction of a wave when going from one medium to another. Okay? Those 3 points, and the syllabus has it a slightly wordier way, but those are the 3 key points in the syllabus, and remember, as the success criteria says, you've got to be able to define these. Okay? Both must occur. If you just have a change of velocity but no direction, it's not refraction. For example, waves going from a deep pool into a shallow pool, but the wave front is parallel with the boundary. They'll change in speed, but they won't change in direction. Right? If we have just change of direction but no speed, no examples that come to mind, then it's not refraction. Now, the syllabus does have this mention of it only occurs when changing mediums, and there are some situations where you might go, well, this is not a change in medium, but you'd be wrong. For example, deep water to shallow water, that's a change in medium because the fact that the depth is so much shorter basically acts as a change of medium. Refraction, you do see it around you, and then you might even have it right there in front of you. Water in a glass, you can get some pretty cool stuff going on here with it. If you put a floating object, it'll look larger floating in liquid compared to outside on the air. And here's a really good one. This dude's head has been disconnected from his body because of the refraction at the edge of the pool. As the light comes in through the air, the water hits his body, then travels out through the glass, compared to here just hitting his head and then bouncing to your eye. So refraction can make some pretty nifty things. Now, Huygens' principle can be used to demonstrate why this happens. I'll talk through this image in a second. What I do need you to understand is that it is not a requirement of the syllabus that you can use Huygens to explain, but I think it is good for you to sort of have this understanding because it gives you more of a deeper understanding of why these things occur. Now, you may also remember from Year 9, or you may find it in the textbook, there is a reference to an equation to calculate how much these things bend. We will look at that when we do light in Unit 4. So if you're thinking going, but where's the refraction equation, where's Snell's law? It's coming later this year. So if we look at this, here we have a set of waves coming in, but this edge of the wave hits the boundary first. Now Huygens' principle says, okay, wherever there is a wave, it's creating circular wavelets. Now that part there, and then it continues to travel down, and this next step hits here, and so it starts to create circular, continues to travel down, hits here, circular, circular. Now, we've only drawn 5 points on here, but every single part of this would be doing the circular wavelets, but if we drew them all, you wouldn't be able to see anything. So we've only got 5 points there, so it's not that it can only happen a certain distance apart. The distance is just there to help you see it. And you can see here that this first wave, okay, is intersecting with this darker grey line here, the first wave of dot 2, and that's intersecting with the first line from dot 3, and the first line from dot 4 there, and the first line from dot 5, so that the new line here is bent compared to the others. If I grab my pen, going here, this point here, oops, didn't draw in too well. Not the greatest drawing, I do admit that. This way ahead. The tablet's been a bit jerky today. Again, so you can see it's just sort of coasting along the edge of the circles. This one here, this one here. Okay. And even though I wasn't looking at that, you can see how these lines are basically all in parallel with each other, and all I've done is taken from where they intercept and draw across to skim along the edge of the circular curves. And so you can see here that Huygens' idea pretty accurately models what we would see, and we would see these waves coming in and then it looked like the waves bend. Okay? Now, we're not covering the law just yet, but the waves aren't bending, they're slowing down. Okay, so it's not that the wave gets here and goes, oh yeah, I'm going to turn to the side, but because the wave as it goes from this medium to this medium, slows down, it looks to bend inwards. If going from this medium to this medium, say this way, okay, sped up, it would bend away, it'd bend the other way. So, but even still, it's not bending, it's just that this bit that got here first is now moving faster, and so the wave circles, because they're continuing to spread outwards from the central point, create this appearance of a wavefront. Okay, so at your core you need to define refraction, but if you can appreciate it in terms of Huygens and his circles, you'll sort of be able to you'll get the background knowledge on a lot more, what's the best way to explain it, you'll get the background knowledge on a lot more wave phenomena and see the connections between them all, and that's a really good thing to have in mind. So that's refraction. Let's head on to diffraction. So Huygens, when he first came up with his principle, couldn't explain diffraction, and Fresnel figured it out and got it rolled into Huygens' principle. Now, I'm not going to explain the core ideas about why, but we just need to know that it explains it. And the core idea is, when a wave hits a slit, we treat this as a new source, and so then the wave will spread to the sides of the gap. So here's an image of it. Here we have a straight wavefront, and it gets to a gap. Now, this stuff here, yeah, that's not a problem, it's just going to create a new wave. But this one here, some of its wave goes to the side, but there's nothing over there to make more point sources to continue the wavefront out, and so it ends up spreading out. It becomes a circular wave at that point, and then that circular wave continues out from it. Okay? So diffraction, we say when a wavefront, where a wavefront will bend as it goes through a gap. That's what diffraction is. It's just the bending of a wavefront when it goes through a gap. Now, to do this, generally the wavelength needs to be similar to the size of the gap. Okay, and as such you can observe it in your day-to-day life with music. Sound has a very large, relative to light anyway, wavelength. The ultrasound is about 17 millimeters or 7 millimeters, and infrasound, so down near the low end of the spectrum, is close to 17 meters. So most of the stuff that we would listen to, sound of my voice, the music, is going to be in sort of that mid-range, in the centimeter regions through to the couple of meter regions. And so that sound will diffract through doorways very easily. If you have some sound source, speaker playing, and those waves reach the doorway, well, they're going to bend quite a bit. There's also apparently a similar thing you can see with looking at your shadow from a very bright light source, and looking at the edge of your shadow, and you may see that there's a sort of bit of fuzziness. Similar idea, but we'll get to why that happens later on in this year. Now, there is an equation that models how waves diffract. Hang on, but firstly, where's my bit? There should be a little bit here about psi. Weird, sorry, I thought I had a note about this. So, let's free talk this for a second. The relationship here happens between wavelength and the size of the gap. So here we have three examples. If you have a very short wavelength with a very narrow or short gap, you see some diffraction. But if you make the wavelengths longer, so the size between waves longer, you see here it bends a lot more than this one here. So longer wavelength, more bending. Okay? But if we make the gap wider now, even though we're still at the same long wavelength, we can see here that the wider the gap, the narrower the bending. And so if we put that together in a relationship, it just looks like this. That if you take the wavelength and you divide it by the distance, the size of the gap, and that will equal the sine of the angle for it bending away from the normal. Okay, so if the gap was infinitely large, there'd be no bending, so let's just talk about how far it's bending off to the side. You don't need this equation. It's not given to you in the syllabus at all. But if you sort of just understand the connection between the ideas, any questions that ask about diffraction, you can use that then to help you out. Okay? Yeah, as I said, it just asks you to find, so if you can explain, you're going to smash it. So, pretty short video today. In this video, we've gone through the following. We've seen that Huygens Principle explains wave phenomena, such as refraction, reflection, and diffraction. We've looked at how refraction involves both the changing of speed and direction of a wave, and we've seen that treating a wave as a point source can explain how diffraction of waves happens when it goes through slits. So your three things you should be able to do, as I said, the first one is the syllabus one. You've got to be able to define these two things. These two here will just help with those other things. For your learning slip your entrance slip for class, please complete questions 1 to 5 in chapters 14.5, and then put those answers into the 3.3.3 space on eLearn. Thanks for listening, guys. Have a great night. Bye.